Hi there. So in this lecture, I'd like to talk about doing an example, showing you an example for the long straight wire of the differential forms for Gauss's law for magnetism and Ampere's law, and how that all works out. So I just want to prove to you that it's true. So if I remember correctly, we covered this some time ago. Let's assume that you have a long straight wire and that there's a current coming out of that wire I. Now, the direction that I'm going to set up for all this stuff is that we have our, let's see, our X, Y, and Z coordinates here, so that our current I is traveling in the plus Z direction for the wire, okay? Now, a natural choice for this is going to be cylindrical coordinates, okay? So we're going to use cylindrical coordinates a lot today. And I just want to remind you of the values for the magnetic field for the long straight wire. Remember, we use the integral form of Ampere's law to find the magnetic field for a long straight wire. That integral form looks like this. The dot product of the magnetic field with the path for an enclosed Amperian loop is equal to mu naught times the current enclosed by that loop. Now, let's say that the radius of our wire is A, and that the current, the total current is I, and it's uniformly distributed across the cross section of the wire. Okay? And so if you took some little slice of that cross-sectional area in one spot and then another spot, if the slices were the same size, the current would be the same. Okay, so let's look at two cases. The first case I'll put here in red, and that's R greater than A. And then let's see, the next slice we'll put here in purple, and that one's for R less than A. So those are our two cases. So let's do the R greater than A case first, right? So there we have the integral of B dot ds. And remember that the magnetic field makes circles around a current of the long straight wire. So the magnetic field here would be going, let's see, if you look down on it counterclockwise with respect to the wire, making loops around it. And what we want to do in Ampere's law is follow that symmetry. And so we're going to do the Amperian loop encircling that current. Our ds would be r d theta around that, right? So here we would have the integral from 0 to 2 pi of b, and then ds would be r d theta. And when you integrate that, you'd end up with 2 pi r b, okay? Now on the other side, you would say mu naught times I enclosed. And the amount of current that's enclosed by that Amperian loop would be all of it, right? So that's just mu naught I. And so what we end up with for our magnetic field is mu naught I over 2 pi r. And that's the magnitude of the magnetic field from a long straight wire. Now, what direction is it? Well, we're here in cylindrical coordinates, okay? So we have r hat, which is the distance radially away from the z-axis. We have z hat, which is the distance along the z-axis from the origin, right? That's in the z direction. And then theta hat would be encircling that z-axis. So b here would be mu naught I over 2 pi r theta hat, okay? All right, now let's do our next case, making that one in purple. So here yet again, we've got I coming out of the page there. And then here is our Amperian loop R, and it's not enclosing all of the current there. So B dot ds, the same argument as before, second verse, same as the first, and I would end up with B times 2 pi R. But now on the other side, it's mu naught times the current that's enclosed by that wire, or I'm sorry, that's enclosed by that Amperian loop. And since we're not enclosing all of the wire when we're inside of it like that, we're only enclosing a fraction. So how much? Well, it would be the amount of the ratio of the cross-sectional areas, because it's uniformly distributed over the area, right? So that would be mu naught I times pi r squared over pi a squared, because that's the fraction of the area of the entire wire that we're covering. You just take a ratio of the areas, and that's what you got. So that would give you mu naught I times r squared over a squared. So now if we set our two sides equal, we have b times 2 pi r equals mu naught I r squared over a squared, and then we can solve. One of the r's cancels out and the 2 pi moves over to the bottom, and so I end up with mu naught I r over 2 pi a squared. And just like before, you would have a magnetic field that is in the theta hat direction. So those are our results for that Ampere's law, okay? Now let's move on and talk about how this would work for the differential forms. We know our magnetic fields now, so let's prove that the differential forms are true. So let's do Gauss's law for magnetism first. Gauss's law for magnetism says that the del dot B is equal to 0. And this is basically another way of saying that there's no magnetic monopoles, okay? Now, how do we prove that this is true for our wire? Well, we have our magnetic fields, right? We have our magnetic fields for R less than A and R greater than A. And so if I plug those magnetic fields into this formula and take that derivative or gradient, then I should end up with 0. So let's see if that's true. Now you can't just go do the straight up Cartesian coordinate gradient operator. You have to do the one from cylindrical coordinates. So you have to remember your Calc 3, or remember that in the back cover of your textbook, Purcell and Morin, the differential forms for the various coordinate systems are written out, okay? So if you look in the back cover of your textbook, you'll see that for a generic vector A, and here A would be equal to AR, R hat, plus A theta, theta hat, plus AZ, Z hat. So this would be in cylindrical coordinates, right? Then del dot A would be equal to 1 over R, the partial with respect to R of R times A of R, plus 1 over R, partial of A theta with respect to theta, plus partial of AZ with respect to Z. So that's how you do the gradient of a vector, the dot product of the gradient with the vector for cylindrical coordinates, okay? Now for our vector, B, the only non-zero component of our vector for either one, see here, is that B theta hat, component, the theta hat component. So we have a B theta that's non-zero, but BR and BZ are 0. So let's apply this formula here to our vector for the magnetic field, okay? So for R less than A, let's do R greater than A first. R greater than A first, right? We had B is equal to mu naught I over 2 pi R theta hat. Now, if we apply this to our gradient operator for cylindrical coordinates, we would have 1 upon R partial of R B sub R with respect to R, and that would be the R hat, plus 1 upon R partial of B theta with respect to theta, right? I'm sorry, there's no hat there. Whoops, losing my mind here. And then plus partial of BZ with respect to Z. Okay, so that's what we have to do. Now, BR equals to BZ is equal to 0 because there are no BR and BZ components here. We just have the theta hat component, right? So this is 0 and this is 0 trivially. Now look, we need to take the partial of B theta with respect to theta. So that here would be del dot B is equal to 1 upon R partial with respect to theta of, now let's plug in our function, mu naught I over 2 pi R. Well, look, there's no explicit theta dependence in that expression, mu naught I over 2 pi r. And because there's no explicit theta dependence, then that means that this is 0. And so del dot B is 0, as we've proven. So check, yes, it's proven. Okay, for r less than a, we have B is equal to, remember here we had it, mu naught I r over 2 pi a squared theta hat. Okay, yet again, BR is equal to BZ is equal to 0. There are no R hat and Z hat components here. Okay, so we can just not write the portions where we have the, the derivatives with respect to BR and BZ. Those are going to be 0 again, right? That's 0 again. So we don't need to worry about that. So let's just worry about this B theta. So we have del dot B is equal to 1 upon r, partial with respect to theta of B theta. Okay, but yet again, 1 upon r, partial with respect to theta of mu naught I r over 2 pi a squared. There's no explicit theta dependence in that expression. And so that means that this is 0 again. Okay, so even though it looks complex, it looks like it is the tricky thing, really it's just all zeros because, the partial derivatives are explicit dependence on those variables, and you don't have that here. Okay, so let's do the differential form now of Ampere's law and prove that that's true. Remember that the differential form of Ampere's law is del cross V is equal to mu naught J. Okay, so that's the differential form of Ampere's law. Okay, so cross products in cylindrical coordinates. Yet again, the back cover of your textbook. And there's a formula for your generic cross product for a generic vector A, and it's del cross A is equal to 1 upon r, partial of AZ with respect to theta, minus partial A theta with respect to Z, r hat, plus partial AR with respect to Z, minus partial AZ with respect to R, theta hat, plus 1 upon R, partial with respect to R, of RA sub theta, minus partial AR with respect to theta Z hat. Okay? So now yet again, that looks really long and scary, but let's think about R functions. Let's do R greater than A first. So yet again, B is equal to mu naught I over 2 pi R theta hat. And that means that the R and the Z components of our vector are equal to 0. Okay? So anything here that has an R and a Z component but no theta component, I can just get rid of. So let's look at it and apply it to our particular magnetic field. So up here I had del cross A is equal to 1 upon R partial AZ with respect to theta minus partial A theta with respect to Z. Okay, so I do have a theta part there, but the Z part is 0. So that's just minus partial with respect to Z of mu naught I over 2 pi R. And that will be my R hat part. Okay, now let's look at the second term, the theta hat term. That's partial AR with respect to Z minus partial AZ with respect to R. So that bit just has R and Z components, and we don't have that here because BR equals BZ equals 0. So I can just say plus 0 theta hat, no problem. Nothing there is going to, contribute. Now looking at the Z hat term, I've got a partial with respect to R, A theta minus partial AR with respect to theta. AR is 0 or BR is 0, right? But we do have a B theta. So I've got a component there, maybe 1 upon R, partial with respect to R of R, and then times B theta, mu naught I over 2 pi R, theta hat. Okay, so now let's see what's going on here. If I look at my r hat term first, I have the partial with respect to z of mu naught I over 2 pi r. Remember, partial derivatives, if there's no explicit dependence, then that means it's 0. So this r hat term is going to be 0 because mu naught I over 2 pi r does not contain z. Now let's look at the, I'm sorry, this should be z hat. I'm making a lot of brain typos today. So if I look at this last term, the z hat term, I've got 1 upon r partial with respect to r. Now let's look at the inside. I've got r times mu naught I over 2 pi r. So that gives me 1 upon r partial with respect to r. The r's cancel, so that's mu naught I over 2 pi. But look, partial with respect to r, mu naught I over 2 pi, those are all constants, so that's 0. Okay? So yet again, everything is 0. Everything's 0. And you're thinking to yourself, wait just a hot minute. That can't possibly be right because, you know, it's supposed to be equal to mu naught j, right? But here's the deal. For r greater than a, there isn't a current there, all right? So there's no current when r is greater than a, okay? So if you get outside the wire, j is 0 out there because, you know, the wire stops at r equal to a. That's it. So this is true. J is equal to 0 for r greater than a. And so that makes sense. Okay. But now let me show you the one thing that's not going to be 0. Let's do r less than a. Okay. Here's the one non-zero thing. Alert, alert, alert. Non-zero-ness coming up. Okay. So on this one, remember that our magnetic field for r less than a was B is equal to mu naught IR over 2 pi a squared theta hat, right? So that was our expression. So now let's do del cross B again, okay? So just like before, I'm only going to have a couple of things that might give me a non-zero value. So that's minus 1 upon r partial with respect to z of mu naught IR over 2 pi a squared. The r hat bit might give me a non-zero component. And then I might get a non-zero component from the z hat part. 1 upon r partial with respect to r of r times mu naught I r over 2 pi a squared z hat. Okay. All right. So yet again, I'm taking the partial with respect to z here of mu naught I r over 2 pi a squared. And there's no explicit z dependence in that expression. So that means this goes to 0. Okay. No explicit dependence for partial derivatives, right? That means 0. So now let's look at the second term with the z hat. Partial with respect to r of r times mu naught I r over 2 pi a squared. Okay, I think we're finally going to have something that's not 0. So I've got partial with respect to r, and then this would be of mu naught I r squared over 2 pi a squared, right? Z hat. Great. Okay, look. Partial with respect to r of mu naught I r squared over 2 pi a squared. So the mu naught I over 2 pi a squared, that's a constant. That can come out front, right? But now I'm taking the partial with respect to r of r squared, and that's z hat. Well, the derivative of r squared is 2r, so that's 2r there. And I'm going to cancel that out with the r that's out front, 1 upon r. So now I also have mu naught I over 2 pi a squared 2r over r, right? So the r's cancel, and that 2 cancels. So I end up with mu naught I over pi a squared. And that is mu naught j. Because J is the current density, which is the current divided by the cross-sectional area, which is I over pi a squared. So we're done. We proved it's true. Okay? So del cross B is equal to 0 when you're outside the wire because there is no current density outside the wire. And when you're inside the wire, del cross B is equal to mu naught J, where J is the current density or the current per unit area. Okay? All right. Well, I hope that helped. I hope it made sense to you, and I'll see you in class.